Convolutions are shift equivariant, meaning that a shift in the input induces the same shift in the output. Equivalently, conv layers preserve spatial relationships between features. However, they are insensitive to other relationships such as rotational and perspectival. For equivariance to more general warps, one needs generalized convolutions. Suppose I take some two-dimensional vector x, then I can equivalently think of the translation tau x defined simply by addition. Now, if I take two vectors x1 and x2, then it turns out that the composite of their translations is exactly the same as translating by their sum. Mathematically, this means that 2D space can be considered as a Lie group of translational warps. Without going into exactly what this means, we can already see how it led mathematicians to generalized convolutions. Our old convolutional formula can be rewritten as an integral over translational warps. More generally, it makes sense to replace this integral over translational warps with an integral over a general Lie group G, for instance the group of all homographic warps. It is then well known that this Lie group convolution is equivariant to arbitrary warps coming from G. There is already a literature on building these convolutions into neural networks. However, all previous works have ruled out warps like homographies. We give the first convolutional framework which can handle any Lie group of warps. Our first task is to equivariantly transform an image into a function on the Lie group. Recall that for an ordinary convolution, the filter is translated across all points in a regular two-dimensional grid, and the response between image and filter computed for each translation. In this way, one obtains a tensor of sampled values, which can be thought of as a discrete approximation of a new, continuous feature map on two-dimensional space. We generalize this operation in warping the filter across a random sample of warps from the Lie group. We compute the response between image and warped filter for each of the sampled warps, and in this way produce a tensor of sampled function values, which we take as an approximation to a continuous feature map on the Lie group. Our formula reduces to the usual convolutional formula if one considers only the group of translations. Importantly though, whereas the usual convolution is not equivariant under general warps, we prove that our new convolution is equivariant under all warps from the chosen Lie group. In practice, we approximate our generalized convolution by a sum over the pixel indices of the image and use a small MLP to parameterize our filter. The generality of our new convolution comes at a cost. To see this, consider a one-dimensional case where the feature and filter maps are both given by a square pulse. When their convolution is taken in the ordinary sense, so that the x-axis indexes translations, the response has a nice property of bounded support, meaning it is zero outside of some bounded set. In contrast, if we take a generalized convolution, regarding the x-axis now as the space of all scaling warps, the response has unbounded support, meaning it can be non-zero all the way out to infinity. We prove that Lie group convolutions continue to make sense even for feature maps with unbounded support, enabling these convolutions in higher layers. To implement them, we first make a change of variables to rewrite our convolutional formula so that the domain of integration is determined by the filter support. This enables a Monte Carlo approximation of the convolution, provided we can sample from a particular probability distribution on the Lie algebra. We prove that this distribution admits a density function, for which we give an explicit formula, enabling sampling via the Metropolis algorithm. We also extend max pooling to our general setting. As I mentioned earlier, our feature maps have unbounded support, so to compute the global maximum of one of our feature maps is practically impossible. Instead, we consider the maximum over only a bounded local region. In practice, we randomly sample a bunch of inputs from the region, compute their outputs, and then use the maximum over these function values to approximate the true local maximum. Importantly, we prove that this local max pooling operation is invariant under warps from the Lie group. Finally, we come to the experiments. We used our theory to build two simple models, AFConv, an affine convolutional model, and HomConv, a homography convolutional model. Each model consists of two convolutional layers and a single pooling layer. Our theory therefore predicts that these models will exhibit invariance under affine and homographic transformations respectively. To test this prediction, we train our models on MNIST and then test on a warped version of the MNIST test set. Our models generalize to the warped data well, with a drop in accuracy of less than 4% each. Both models compare favorably to benchmark capsule-based methods for invariance, with HomConv in particular achieving state-of-the-art. Thank you.